So water is something that is extremely important. You can't have life without water, right? So we use water every day. Most of us probably washed at least some part of our body with water this morning and drank something that, if not being just tap water, it had water in it, right? Coffee or tea or soda or something. Very important. It's the most important liquid on our planet. It's also the most common. But it's also a very extraordinary substance. Extraordinary, very unusual substance. It has a low molar mass, 18 grams per mole, and yet it is a liquid at room temperature. And that is due to its high, very strong intermolecular forces. It has hydrogen bonding, and so water molecules are very attracted to each other. It's the main solvent in living organisms. Your body has a lot of water in it. Plants have a lot of water in them, and that is the solvent in which reactions occur. It has a very high specific heat capacity, and so that moderates our climate. We talked last week about temperature changes in the valley versus in San Francisco, and how here in the valley the temperatures change much more dramatically because we have less moisture around to moderate the temperatures. Another strange thing about water is it expands upon freezing. Most substances, when they go from a liquid to a solid, actually contract. They get smaller, not water. And the effect of that is what we see here with this head of lettuce. Take a head of lettuce and you stick it in the freezer, and it's not good for the lettuce. It's going to get all nasty and shriveled up, because what happens is, as the water freezes, it expands and it ruptures all the cell walls in the lettuce. And you let that thaw out, and it's just going to be a pile of mush. It's nasty. So here's a graph similar to one we looked at earlier in this chapter. This one's just a little more, got more information on it. So here we're looking at the boiling point versus the period in the periodic table. And so here in the blue, we have the group 6 elements. We've got oxygen, sulfur, selenium, and tellurium, and we're looking at their compounds with hydrogen. And so we see trend here, right, that as the period increases, which corresponds to an increase in molar mass, the boiling point goes up. But water breaks that. Period, what's that, 6, 7? Yeah, period 7, with the halides in the green here. We see a trend as well, but then for hydrogen fluoride, it's much higher. And then we look at group 5 in the yellow, and we see this nice trend here as well, except for ammonia. And then group 4, these guys all stay in a nice trend. Why do these guys break the trend? Hydrogen bonding. ET phone home, right? So here we have fluorine, oxygen, and nitrogen bonded directly to hydrogen. And so between ammonia molecules, there's an extra strong force called hydrogen bonding. Between hydrogen fluoride molecules, between water molecules. That causes their boiling points to be much higher than predicted. Nope, didn't need to do that. I wanted to get rid of this line because it's making things hard to see. There's a trend here as well. We see that the blue is higher than the yellow, than the green, than the orange. The group 4 elements here are forming nonpolar compounds. There's no lone pairs on the central atom. So they're going to have the lowest boiling points. As we go up here, we're going to have polar molecules, and so they're going to have dipole-dipole forces that are going to cause the boiling point to be higher. So we do see that trend, but then these completely buck everything else. Just based on this trend, we would expect water to have a boiling point of maybe minus 75 degrees Celsius. So that would mean that at 25 degrees Celsius, all water would be in the gas state. All the oceans, all the water in your body, you can just kind of imagine how that would be. Water's really important, and so water pollution is definitely a concern. I'm not going to test you on this, but I would like you to have an idea of the different kinds of water pollution. So you can have biological contamination, or you can have chemical contamination, and the way you treat those is going to be different. Biological contaminants are microorganisms, and those can make you very sick. That's commonly going to get into your water because of animal waste or human waste. The microorganisms in that waste can contaminate the water. So biological contaminants can be treated. A lot of them can be killed just by boiling the water. So you boil the water, kills all the bugs in it, and then you can drink it. Some organisms will still live, and so that's just not enough. An alternative to boiling is using a chemical of some sort, like bleach or something, to kill the microorganisms. And then you have chemical contaminants, and these come from pesticides, household chemicals, industrial chemicals, oil dripping from your car, radiator fluid running into the river, etc. Most of these are non-volatile. They are not alive. We can't get rid of them by boiling, right? Boiling is not going to destroy them. It's not going to cause them to evaporate out of the water. Killing them, they're not alive, so we can't kill them. So boiling doesn't do any good. In fact, if you boil the water for a significant amount of time, you're reducing the volume and actually concentrating the chemical contaminants. So what can you do with chemical contaminants? Well, there's a variety of filters that can be used. So water purification uses things like reverse osmosis or charcoal filters, various things like that.